Right, so let's start. So we were talking about relational schema design the last class, right? So we introduced the notion of functional dependencies and how functional dependencies are a useful way to encode important properties about the data that you're capturing within your database, right? So that was a useful way to encode certain constraints, encode certain properties about your data. And then we launched into a little bit of sort of a better understanding of how to derive these functional dependencies and how to work with them. And one of these things that we looked at was the aspect of closure. So this is a concept that we studied where given a set of attributes and a set of functional dependencies, and you want to find all other attributes that are inferred or derived or implied given this set of attributes, right? So it was basically all attributes that are in some sense dependent on this set of attributes. So the closure of a set of attributes is denoted with this plus superscript here, and so basically you use that to denote the closure of a set of attributes. And the mechanism to do this closure or find this closure is you start with the set of attributes that you want to operate on, assign it to a set X, and then you repeatedly check if a certain functional dependency applies such that the left-hand side is in X and the right-hand side is not in X. So then you can go ahead and add the right-hand side to X, and you keep doing this until you can't do it anymore. Okay, so this was the algorithm for closure. There are two uses for attribute closure. The first is to test if something is a super key. Remember, a super key was a superset of a key, something that contains a key but possibly contains more stuff. To check if something is a super key, you simply compute the closure of X and then check if X plus contains all of the attributes of R. Okay? To check if X implies Y or X determines Y holds, you do something similar. You once again compute this X plus, and then you check if Y is contained within that or not. If Y is contained within that, you know for a fact that X implies Y holds. If it is not contained within that, then you know that it doesn't hold. Okay, so attribute closures are a convenient way to check if a certain functional dependency holds, or if you want to check if a certain set of attributes is a super key. So let's, I've never seen this symbol before. Have you seen this symbol before? Okay, anyway, so let's talk about potentially how to derive whether certain functional dependencies hold or not hold. So let's say I want to, I have these speculations. Okay, so if A implies B, then B implies A. What I want to do is to disprove these speculations. So if A implies B, then B implies A. Can you think of an example where that doesn't hold? Any ideas?
Do you just want like a language example?
Just like a real world example. If A implies B, then B implies A is this, yeah.
If it's raining, then it's cloudy.
If it's raining, then it's cloudy. If it's cloudy, then it's not raining. Sure. Yes.
If you say if it's cloudy, then it's raining, that's not necessarily true.
Sure, sure. So yes, so that's a perfectly valid functional dependency if you are encoding those attributes as data. Maybe a little bit more boring would be something like SSN implies name, but maybe name doesn't imply SSN if there are multiple people with the same names. There are often multiple John Smiths in the US, so that's probably true. In which case this functional dependency, so name to SSN doesn't hold, but SSN to name holds. Okay? So can we come up with a counterexample for this guy? So if AB implies C and A implies C, then B implies C. Again, I'm looking for a real world example. Yes?
If SSN and age implies name,
Yep.
then yeah.
Okay, so A is SSN, age is B, and C is name. And you also have SSN implies name, but you don't have age implies name, right? Obviously enough. So that's a perfect example. Okay? Cool. So often there are two ways of trying to infer whether a functional dependency holds given a set of functional dependencies. One easy way of disproving that a functional dependency holds is to come up with a counterexample. These are all convenient counterexamples that show that these functional dependencies do not hold. Okay, so the generalizing this notion of a closure, we talked about the notion of a closure of a set of attributes. What about a closure of a set of functional dependencies? A closure of a set of functional dependencies basically contains all functional dependencies that are logically implied by a given set of functional dependencies. Okay? So why would we care about doing a closure? Well, it allows us to answer all possible questions of the following type, which is this functional dependency F logically implied by S? Okay, so you have a set of functional dependencies S, and you want to check whether a given functional dependency F is implied or not. So to do that, one way of doing it is to compute the closure of the set of functional dependencies. This is expanding S out into all functional dependencies that are implied from S. Okay, so let's walk through a quick example before we get into the algorithm. So let's say I have this relation R. I have a bunch of functional dependencies. So S contains A implies B, A implies C, CG implies H, CG implies I, and B implies H. Intuitively, would you guys be able to tell me whether A implies H, is that logically implied or not? And if so, why? Yes? A implies B and B implies H. Right. So if there are two tuples, again, you can think through this intuitively, right? If you have two tuples that have the same value for A, then they have the same value for B because A implies B. And because they have the same value for B, and since B implies H, they have the same value for H. And therefore, sort of going back to the start, if two tuples have the same value for H, for A, they have the same value for H. Okay, so you're basically chaining this guy with this guy to get you the desired functional dependency. Now, so this seems a little ad hoc, right? We shouldn't have to sit and think about these examples or these intuitions. There should be a more rigorous or a more formal way of deriving whether a functional dependency holds or not. And that's the next topic. Okay, so so the next topic is to come up with a set of rules that allow us to derive functional dependencies. So to put this in context, if we want to check if a specific functional dependency is true, we have an algorithm for that. We have a way to compute the closure of the left-hand side, so A plus, and then check if B is contained in it. So we have that already. In order to compute all A implies B that are implied by a given set of functional dependencies, that is, if we want to compute the closure of a set of functional dependencies, we require an algorithm that derives from this framework which is called Armstrong's axiom. So these are properties of or rules that you could use to derive new functional dependencies given a set of functional dependencies. So what do these Armstrong's axioms look like? So they are actually pretty straightforward. The first axiom is actually trivial. The first axiom basically says if you have A1 through AN on the left hand side, that certainly implies a subset of A1 through AN on the right hand side. So this is what is called as the reflexivity rule. Okay, very straightforward. If tuples have the same set of two tuples have the same set of values for A1 through AN, then they obviously have the same set of values for a subset of those attributes. Right? Okay. Augmentation rule, the second rule, basically says I can tack on stuff on the left hand side and on the right hand side and it'll still hold. So if I have A1 through AN implies B1 through BM, then A1 through AN plus C1 through CK implies B1 through BM plus C1 through CK. So I've added the same thing on the left hand side and the right hand side. Once again, this holds. Why? We can argue this because if two tuples have the same set of values for A1 through AN, then they have the same values for B1 through BM. If two tuples have the same value for A1 through AN and C1 through CK, then because of the A part, they have the same value for B1 through BM, and because of the C part, they have the same value for C1 through CK. Okay? So if you add the same set of attributes to both sides, the rule still holds. The functional dependency still holds. The last one, and perhaps the most interesting of this lot, both of these are fairly straightforward. The most interesting one is the transitivity one. So this is what we applied in the previous example as well. So if you have A1 through AN implies B1 through BM, and B1 through BM implies C1 through CK, then A1 through AN implies C1 through CK. Okay, it's simple transitivity. It's basically A implies B, B implies C, then C implies A. Then A implies C. Okay? That's it. Any questions about the Armstrong's axiom? These should be fairly straightforward. But if you have any questions, stop me now. Okay? All right. So, how do we infer the closure of a set of functional dependencies using Armstrong's axioms? Well, the way to do this is the following. You start with the set of functional dependencies that you have, and then you loop until you can't get any more rules. And within the loop, what you do is for each functional dependency in the current set of functional dependencies that you've identified, you apply the reflexivity and augmentation rules. You add those new functional dependencies to S plus, and for every pair of functional dependencies in S plus, apply the transitivity rule. You add the new functional dependencies to S plus. So you basically repeatedly apply the reflexivity, augmentation, and transitivity rules. That's enough. That's what this algorithm says. Okay, so repeatedly apply these guys, and then you'll get all of the functional dependencies that you would that are implied by the current set of functional dependencies. Any questions about this? So you just repeatedly apply these guys, and then you get the closure. Okay. One issue with this, one issue with the overall goal of computing the closure of functional dependencies is that this procedure could lead to lots and lots of rules, right? So let's say you have n attributes, and this is something we covered the last time as well. If you have n attributes with just one functional dependency valid, A implies B, then by just applying the augmentation rule, you could get an exponential number of functional dependencies. Why? Well, you take A implies B, right? You could add any subset of attributes on the left hand side and add the same subset of attributes on the right hand side, and you have a new rule, right? So if you have n attributes in total, 2 of which are A and B, so basically you can subselect up to n minus 2 attributes here, and each of those, if you decide whether to keep them or not, you have 2 times 2 all the way up until 1 last 2 for the n minus 2th guy. So overall you have 2 to the n minus 2. Okay? So, so this is exponential, right? So if you basically have even just one functional dependency, you could derive a very large number of functional dependencies using this closure algorithm. So this is not something you want to apply lightly, right? So you don't want to do this unless you absolutely need it. Okay? Any questions? Okay. So There were two simple rules that we talked about in the previous class, and let's see if we can rederive them using Armstrong's axioms. So let's try to, we had one trivial rule. This was the same as reflexivity, so let's not worry about that. And the other two rules, which I'm going to introduce again, are the splitting and combination rule. So this is the combination rule, and this is the splitting rule. Okay? Combination rule says if x implies y, x implies z, then x implies yz. The splitting rule says if x implies yz, then x implies y. Okay? So let's try to derive the first guy using Armstrong's axioms. Okay, so I have x implies y and x implies z, and I want to derive x implies yz. So any guesses on how I would apply Armstrong's axioms to get this? So let me start with a hint, right? Doesn't look like we can apply transitivity because these two guys don't have the same left-hand side and right-hand side combination, right? So for us to apply transitivity, they should share one of them, one of the rules left-hand side should be the same as another rule's right-hand side. So we can't apply transitivity yet. We can't apply reflexivity either because all of the rules already have just one attribute on the left-hand side. So we have to apply augmentation in some way. So what way should we apply augmentation? Yep.
Maybe say xz implies yz.
Xz implies yz, sure. Sorry. All right. Seems like a reasonable first step. What next? Yep. Anyone? Okay, so let's go back and look at what we need, right? So we need x implies yz. We've already gotten the yz part on the right-hand side. So if we want to think about applying the transitivity rule that ends up with us having yz on the right-hand side, we want something that ends up with xz on the right-hand side so that we can apply the transitivity rule, right? So how do we get xz on the right-hand side? Okay, another hint. It is to do with applying augmentation to this. What should I do to this rule? Yep.
We can augment it with another x implies,
So you're correct. I mean, you could augment it with x on both sides, right? So if you augment it with x on both sides, it is basically x implies zx, but xx is basically just x, right? So x implies zx or xz, right? It's the same thing. So since x implies xz and then xz implies yz, you can apply transitivity and you have x implies yz. Is this clear? Is this clear or is something not clear? Okay. All right. So what about this one? X implies yz, then x implies y. Yep.
yz implies y, so we can use transitivity to say that x implies y.
Absolutely. So yz implies y. Why is that? Huh? reflexivity, right? So YZ implies Y. So this is via reflexivity. And since we have YZ implies Y, that with X implies YZ, you have applying transitivity, you have X implies Y, right? Any issues with this, or is it fine? All good? Okay. Cool. So this was a set of concepts regarding functional dependencies, functional dependency closures, and attribute closures. Okay. So with these notions, let's go back to our original question on how to design good schemas. We'll describe various notions of what it means for a schema to be good. Okay, so the first notion is this notion of Boyce-Codd normal form. And remember, I had mentioned this, that there are various ways of decomposing a set of relations to give you smaller relations. And that decomposition process is a process called as normalization. And there have been a bunch of different normalization methods that have been prescribed. These are 5 of them, and these normalization methods are called normal forms. Basically, they describe what the eventual criteria for the decomposed relations must satisfy. The first 2 normal forms are not something we're going to cover. These are not no longer interesting, no longer considered to be relevant. The next 3, in fact, maybe just these 2 are the ones that we're going to cover in class. So let's start with the Boyce-Codd normal form. Okay, so the Boyce-Codd normal form is actually very easy to understand and very intuitive. The Boyce-Codd normal form says that a relation R is in Boyce-Codd normal form if and only if whenever there is a non-trivial functional dependency A1 through AN implies B, then A1 through AN is a super key for R. Okay, so whenever there is a non-trivial functional dependency, the left-hand side of that functional dependency is a super key for the relation. It is a superset of a key for that relation. Otherwise, the relation is not in Boyce-Codd normal form, and we have to decompose it further. Okay, so in a perhaps more colloquial way, when rather than formal way, when a set of attributes in R is determining another attribute, then it has to determine all of the attributes. Okay, so you can't allow a set of attributes in R to determine just a subset of all attributes. You have to let it determine all of the attributes. Otherwise, the relation is not in Boyce-Codd normal form. Okay, so let's try to again get some intuition for this. So let's say you have a relation R with ABC, and AB is the key, okay, but at the same time there's a functional dependency A implies C. Okay, there's a functional dependency A implies C. If there's a functional dependency and A implies C, then implicitly C is being repeated for multiple A's. Okay, so let's say you have SSN, I don't know, what is a, okay, phone number and name, let's call it. Okay, so SSN implies name. Okay, and SSN plus phone number is a key for this relation because a person can have multiple phone numbers. But because of this function dependency A implies C or SSN implies name, the same name is being repeated multiple times for each phone number, right? So the same name is being repeated multiple times for each phone number, and this could lead to various anomalies later on. There is redundancy, there is update anomalies, there is deletion anomalies. These are the 3 anomalies that we had seen earlier, right? So because of the redundancy, this could lead to anomalies. So the intuitive reason for why we want relations to be in Boyce-Codd normal form is so that we can minimize this kind of redundancy, and therefore we can minimize these kinds of anomalies. Okay? So this was the example that I mentioned. You have a relation here with name, SSN, phone number. The dependency is SSN implies name. Is the left-hand side, so let's check if this satisfies Boyce-Codd normal form. Well, is the left-hand side of this functional dependency a super key? No, because the only super key here are SSN phone number or SSN phone number and name, right? These are the two super keys. Basically, SSN phone number is a key, right? And any superset of that is also a key. So therefore, this is also this is a super key. Okay, so is the left-hand side of this dependency a super key? No, because it misses phone number, and therefore this is not a super key. And because of that, this relation is not in Boyce-Codd normal form. It's not in BCNF. Okay? All right, so on the other hand, if I decompose it into these two relations, one corresponding to SSN and name, and another corresponding to SSN and phone number, then is it in BCNF? Well, yes, because if you look at this functional dependency, the left-hand side is SSN. SSN is now a super key of this relation, right? It is in fact the key for this relation, and therefore it is a super key. And because of that, this relation is now in Boyce-Codd normal form. Is this relation in Boyce-Codd normal form? Trivially, yes, because there are no functional dependencies that apply to this relation. Right? Since there are no functional dependencies that apply to this relation, it is trivially in Boyce-Codd normal form. Okay? Any questions about this? Takes a while to get this concept. So, any questions about this? Okay. So, let's walk through more examples to help you understand the concept. So, in transforming a relation that, or a schema that violates Boyce-Codd normal form to one that satisfies Boyce-Codd normal form, what you need to do is to decompose. You need to start with a larger relation, decompose, decompose, decompose until you get to a schema that satisfies Boyce-Codd normal form. Okay? And the criteria for decomposition is you first find a dependency that violates the BCNF condition. Okay? Find a dependency that violates the Boyce-Codd normal form condition. What that means is you have a non-trivial functional dependency such that the left-hand side is not a super key. Okay? So the left-hand side is not a super key, but this functional dependency still holds, right? So, so once you have that, then the way to decompose is to first choose the right-hand side to be as large as possible, so expand it out by applying functional dependencies, and then you decompose it into two relations, one R2 and one R1. R1 will contain all of the A's and all of the B's, and R2 will contain all of the A's and all of the others. So why is this sufficient? Well, the reason why just breaking it up into these two relations such that the A's are in common is that the A's allow you to connect the tuples in the two relations if you want to reassemble the overall relation. Okay, so you started with the relation and you're decomposing, right? But one concern is when you are assembling the old relation again, are you missing or losing information or adding additional information? Well, in this case, that is ensured that that doesn't happen because you have a set of attributes that are in common between these two relations. These are the A's that will help you connect the tuples in the two relations. So it will help you connect the B's with everything else, right? Because you have the A's in common. Clear? Okay. So let's see how these decompositions look like. So let's say I have a relation with name, SSN, age, eye color, and phone number. My functional dependency is only SSN implies name, age, eye color. Okay? So can you guys give me an example of a key for this relation? What's a key for this relation? Even before we get into BCNF. Yep.
SSN.
Just SSN? I think you're missing an attribute. Is there an attribute that you're missing?
Name.
So SSN implies name. So we are not concerned about name, right? So SSN already implies name, age, and eye color. So are there any attributes that you're missing? Well, you're missing phone number, right? So in order to identify a key for this relation, you would need both SSN, because SSN implies name, age, and eye color, but you would also have to include phone number. It has to be SSN as well as phone number, because phone number is not implied from SSN. Right? Since phone number is not implied from SSN, SSN plus phone number becomes a key for this relation. Does that make sense? So once again, what is the definition of a key? A key is a set of attributes that determines all the other attributes. SSN helps you determine name, age, and eye color. Correct? So since SSN helps you determine name, age, and eye color, what is the remaining attributes apart from these four attributes? Well, there's phone number, right? SSN does not determine phone number. But together, SSN and phone number will determine all of the other attributes, right? So SSN and phone number will determine name, age, eye color, SSN and phone number trivially. Correct? Okay. So SSN comma phone number is your key for this relation. Okay? All right. So going back to this functional dependency, you have this one functional dependency. Is this relation in Boyce-Codd normal form? No, why is that? SSN is not a super key, right? So you know that any super key for this relation has to contain SSN and phone number, right? A super key is a superset of a key. Your key is SSN plus phone number. Left hand side is not a super key because it misses phone number, right? Because of that, this functional dependency is a violation. It indicates that this relation is in violation of the Boyce-Codd normal form property. So how would I decompose it? Any guesses? Yep. So I want to decompose this into two relations. So why would we apply augmentation again? Okay, all right. So starting with this, I have a rule which is non-trivial and violates BCNF. So what I can possibly do is I can use this rule, and then I can divide the set of attributes in this relation into two sets. I have SSN here, and the name, age, eye color here. Okay? This is one set. And then I have another set which is phone number. Okay? So basically I take this functional dependency and I create one relation out of it which contains SSN, name, age, eye color. And what is left? The only attribute that's left is phone number. Okay? I can't make a relation just out of that. I need to connect that to the other relation. In order to connect it to the other relation, I include the attribute SSN. So the two relations are SSN, name, age, eye color. And this is just from this functional dependency. And the other relation is SSN, phone number. Okay? And the reason why I kept SSN around in the other relation is so that I can relate the tuples in the two sides with each other. If I had just decomposed it to a phone number, I won't be able to recreate the original relation anymore. Okay, so that's why I've kept the SSN here, not gotten rid of it. Okay, so now I have these two relations. Is this in Boyce-Codd normal form? Well, it is, because the only functional dependency that applies to this is this functional dependency, right? SSN implies name, age, eye color, and trivially that is in Boyce-Codd normal form because SSN is a super key. It's a key for that relation and therefore a super key, and therefore we are in good shape with that relation. The other relation is SSN and phone number. There are no functional dependencies that apply to that relation, and therefore it once again is in Boyce-Codd normal form, and therefore you have the decomposed relations are in Boyce-Codd normal form. Okay? All right, so here's a slightly more complicated example. I have two functional dependencies. SN implies name, age, eye color, and another functional dependency which is age implies draft worthy. Okay? So how would I, so firstly, is the relation in Boyce-Codd normal form? No, why is that? Anyone? Maybe not you, since you've been answering a lot. Thanks for that. Anyone else? Yes?
The left-hand side of both equations aren't super keys.
Correct. The left-hand side of both functional dependencies are not super keys, right? So SSN is not a super key, nor is age. Correct? So what is a key here? Well, in this case, the keys are the key for this relation would be SSN, maybe, and actually it's just SSN and phone number, right? Once again, okay. So that's a key for this relation. Neither of these two are left-hand sides are a super key, right? And therefore, these relations are not in Boyce-Codd normal form. So how do we decompose it? So the first step would be, let's say I want to decompose it using this rule. Okay, so I've decided to decompose it using functional dependency 1. If I want to decompose it using functional dependency 1, the first thing that I would do is I would try to beef up the right-hand side as much as possible. Okay, so the right-hand side now contains name, age, and eye color. Can I add any other attributes to the right-hand side? Well, I can apply functional dependency number 2, right, which is age to draftworthy. So I now have SSN, oops, I now have SSN name, SSN implies name, age, eye color, and draftworthy. Right, so this is, if I were to take SSN and apply the closure to it, this is the set of attributes that I'm going to get. Correct? So now I have a functional dependency that has expanded out on the right-hand side as much as I possibly can. Now I'm ready to apply a decomposition. So I will take this functional dependency and I will create a relation out of it. So I will have SSN, name, age, eye color, and draftworthy. That's my relation 1. What will be in the other relation? Yep. SSN and phone number. And the reason we are okay with splitting this up is because SSN is in common, and therefore that allows us to connect the tuples in the two relations. Okay. Now, is this set of relations in Boyce-Codd normal form? Let's start with relation 1. Is relation 1 in Boyce-Codd normal form? Okay, let's go even one step slower than that. Let's take relation 1 and I want to check whether it is in violation of Boyce-Codd normal form via functional dependency 1. Is it in violation of Boyce-Codd normal form via functional dependency 1? Yep?
No,
No? And why is that?
because now the key for functional dependency one would just be SSN.
Perfect. So now the key for this relation is just SSN, right? SSN implies the rest of the attributes. And because SSN implies the rest of the attributes, R1 is not in violation of Boyce-Codd normal form via functional dependency 1. So it's not in violation via functional dependency 1. Is it in violation via functional dependency 2? Yes, no, maybe. What do we think? So what is the once again, what is the condition for something to be a violation of Boyce-Codd normal form? The condition is that it's a non-trivial functional dependency and the left-hand side is not a superkey, right? So your functional dependency is age implies draftworthy. Is age a superkey? No, right? Age is not a superkey because it doesn't imply all of the attributes. It only implies draftworthy. So R1 is in violation of Boyce-Codd normal form via functional dependency number 2. Okay? So how would we decompose it? Okay, so R1 goes away. I want to decompose R1. What would I get? Yep.
I actually have a question.
Yes.
So we have SSN implies age.
Uh-huh.
Age implies draftworthy.
Uh-huh.
So wouldn't SSN imply draftworthy then?
SN does imply draftworthy.
So why? I'm having a hard time understanding then why this is violating.
Good. Okay. So for functional dependency number 2, that has age implies draftworthy. Okay. So that's your functional dependency. For this functional dependency, it's a non-trivial functional dependency, so this is something that we should consider. The left-hand side is just age. So is age a superkey or not? Age is not a superkey, right? Because age implies draftworthy, but it does not imply SSN, does not imply name, does not imply phone number. Right? So age is not a superkey. And because of that, this functional dependency violates the BCNF property for this relation. And therefore, we have to break it down further. Okay, so even though this relation does satisfy the Boyce-Codd normal form via one functional dependency, it doesn't satisfy via the other one. Right? So it satisfies via functional dependency 1, doesn't satisfy via functional dependency 2, so you still have to break it up. The motivation behind why we break it up is this second functional dependency leads to redundancy. Right? The second functional dependency is basically saying that draftworthy is going to be the same for all tuples that have the same age. Okay? Since that information is repeated multiple times, I can take it out and keep it in another relation. Right? So any violation is an opportunity for me to decompose further. In this case, I have a violation via age implies draftworthy, so I'm going to decompose it further. Okay? Okay, so where were we? So we wanted to decompose this. So what are we going to get as a result? What are the two relations that I'm going to get from R1 when I decompose via age implies draftworthy? So I'll give you the answer. So let's say this is R3 and R4. So one of the two so if you take age and try to find its closure, you're not going to find anything else apart from draftworthy. Draftworthy is the only attribute that age implies. So I can take this functional dependency, which is a violation, and have that directly be a relation. So I can have age and draftworthy. Okay? The other relation, on the other hand, would have the remaining attributes, what are the remaining attributes? I have SSN, name, eye color, right? So these are the other attributes in here. And to connect these two relations, I still need age, right? So that attribute stays in common between these two relations. Okay, so this is now my Boyce-Codd normal form. You can go and check whether there are any other functional dependency violations, and you'll find that there are no more. So this is indeed my final Boyce-Codd normal form decomposition for this. Okay. All right. So the interest of time, I'm going to skip over a couple of these examples. I encourage you to go try these out. If there are any questions, just send us a note on Piazza. So there are two examples in the slides corresponding to movies and with different kinds of functional dependencies. So go try it out for yourself and see if you have any issues. The answers are also in the slide, so you can verify your answers. Okay, and let us know if something is off. Okay, so the last step in completing the story before I describe the algorithm is in two attribute relation. So let's say you have you have a relation which has only two attributes, A and B. The claim is that any relation with two attributes is automatically in BCNF. And why is that? So let's walk through various cases. So if there are no functional dependencies, then trivially the relation is in BCNF because there's nothing to violate. Okay, if there are no functional dependencies, you're in good shape. Let's consider the three other cases. So the three other cases is A implies B is true, B implies A is not, B implies A is true, A implies B is not, and A implies B is true and B implies A is true. So these are the three cases that we need to consider. For the first case, if you have A implies B does not violate BCNF because A is a superkey for this relation, right? Because A implies B, therefore A implies all of the attributes of the relation. And therefore A implies B does not violate BCNF. This case of B implies A is symmetric. So the only case that I need to worry about is the final case, which is if A implies B is true and B implies A is true. In this case, both A and B are keys, and therefore neither of these two rules violate BCNF. Okay, therefore all two attribute relations by default are in BCNF. Okay, so that makes it easy for us to figure out when to stop running this algorithm. Okay, so this is the BCNF decomposition algorithm. We intuitively described it, but here is a more formal description. The description says you have an input relation R, a set of functional dependencies. S, check if R is in BCNF. If R is not in BCNF, pick a functional dependency violation. A implies B. Okay. Then compute the closure on of the left hand side. So you expand it out as much as you can. And then you create two relations, R1 which is the closure of A, and R2 which is A union with everything else. Okay, so A union with the rest. So R minus the closure of A. So this is everything else, and you still have A here so that you can connect these two relations with each other. After that, you compute all of the functional dependencies that are valid over R1 using the original relation and the set of functional dependencies. And similarly, you find all the functional dependencies that hold over R2. And then you repeat recursively for each of those two relations. Then you stop when all of the relations are guaranteed to be in BCNF or are two attribute relations. If they are two attribute relations, the previous slide we proved that they are by default in BCNF. Okay, so this is the overall algorithm. Any step unclear? Anything that's confusing? Okay. All right. So So another question that you might have is this BCNF decomposition unique? As it turns out, it is not. There are multiple decompositions that you can arrive at by applying the algorithm on the previous slide. So let's say you have a relation R with SSN, net ID, and phone. And your functional dependency one is SSN implies net ID. Net ID implies SSN, so your second functional dependency. Each of these two functional dependencies violates BCNF because SSN is not a superkey, nor is net ID a superkey. Okay? So, can you tell me two different BCNF decompositions for R? SN. Okay, so why don't we talk about which function dependency you're using to break it up? Okay, you're using FD1. Good. So what are the two relations that you get? Okay. SSN net ID. Yep. Yep. That's totally fine. So that's one. What's another one? Be someone else? So basically we started with this guy and we ended up with this decomposition. What do we start with this one? Net ID implies SSN. Yep.
Net ID and phone.
Yep. As net ID and phone, SSN and net ID. Yep. Okay, so by choosing to apply one of these two functional dependencies, first you get a different decomposition. Okay, and then why do we know we are done when we get these relations? Well, two attribute relations are in BCNF. Right? Since two attribute relations are in BCNF, you know to stop, you don't need to go any further. Okay. Cool. So, so now that we know how to compute these BCNF decompositions, let's step back and talk about the properties of BCNF decompositions. So the first property is that BCNF removes certain types of redundancies. These are the redundancies that are caused by adding many to many or one to many relationships. Those sorts of redundancies, as well as internal redundancies within an entity set caused by functional dependencies between the attributes of an entity set, these types of redundancies are all removed via BCNF. So BCNF removes these redundancies, making it less redundant. So it tries to decouple these relations, break it down such that there is very little redundancy that's left behind at the end of it. So that's one property. BCNF tries to remove certain types of redundancies. There's one type of redundancy that it doesn't remove. This is called the multi-valued redundancy. This is not part of our syllabus. If you're curious, you can go take a look at the textbook. BCNF also avoids information loss. Okay, this is an important, extremely important property because basically information loss, this property guarantees that you can reconstruct the original relation instance from the decomposed relation instances. So basically what this says is even if you decompose the relation into multiple relations, you are neither losing information nor are you adding spurious information. Okay, there is no information loss, nor are you adding junk information that shouldn't exist. Okay, so the same set of information is there in the original relation and in the decomposed relations. This is important, right? You don't want your decomposed relations to introduce new data or new aspects that are not found in the old data, right? Or you don't want them to lose information that was found in the old relation. Okay, so you don't want either of those things. And well, how do you reconstruct the original relation? So let's say you've started with RABC and you decomposed it into RAB and RBC. Well, you would just do a natural join of those two relations and then you can reconstruct the original relation. why does the natural join work? Well, you have basically ensured that there is some attributes in common between these two relations. Those attributes in common will help you connect the tuples in those two relations such that a natural join can be computed and you can reconstruct the original relation. Okay? How do you decompose a relation into these two relations? Well, you just apply a projection, right? You apply a projection down to those attributes and that's fine. Okay, so project down, join on the way up. Okay, so if you start with the original relation, want to break it down, you use projection. If you want to reconstruct the original one, you use a natural join. Okay, so to give you a little bit more intuition about this losslessness property, let's talk about what would happen if we didn't worry about ensuring that there are some attributes in common between the relations that we decompose. Okay, let's talk about what would happen. So this is let's call it a worst case scenario. So what if we break up stuff without worrying about preserving attributes across the broken up relations? For example, let's say I have a relation R which has A, B, C, D, E, and I go ahead and break it down into R1 containing AB, R2 containing BC, R3 containing CD, and R4 containing DE. Okay? I know that two attribute relations are not in violation of BC and F. Also, I've ensured that there are some attributes that are in common across these relations, so I can actually do a join. So why should I bother with doing this complicated BC and F decomposition algorithm when I can just take this original relation, just decompose it into two attribute relations and be done with it, right? So why do I care? So as it turns out, just willy-nilly decomposing these relations into two attribute relations leads to information loss. Okay, you lose information if you do this. Why is that? Okay, so I have this original relation which is ABC with values two tuples, one with values 1, 2, 3, another with values 4, 2, and 6. I've decomposed it into two relations, one corresponding to AB, one corresponding to BC. So the AB relation has tuples 1, 2, and 4, 2, and the BC relation has tuples 2, 3, and 2, 6. Okay, how did I get this? Well, I simply did a projection, right? I did a projection, I got this. Okay, so when I take these two relations and then I try to reconstruct this via a natural join, what would my result look like? What are the tuples that are going to be in my result? Yep. 1, 2, 3. Mm-hmm. 1, 2, 6. Mm-hmm. Right. Right, so you did decomposition by doing projection, but when you did a natural join, you're not actually getting back the original relation, you're actually getting back more stuff. For instance, you got back this guy even though it was not in the original relation, you got back this fellow even though it was not in the original relation. Right, so you got these two spurious tuples that are not in the original relation because you just went ahead and decomposed without worrying about it. Right, so this is a cautionary tale which says that you can't simply go ahead and decompose into two attribute relations and hope for the best. You have to be careful when you decompose because you are going to get back potentially more information than you started off with. Why did I say more information than I started off with than less information? So I can guarantee that I'm always going to get back the same information plus additional information. Why is that? Give me an intuitive explanation rather than something formal. Yep.
Because it's like natural join or just join with each of like the tuples, it's like you're getting back like a multiplication of it, so you can't get less than what you already have.
Right. So put another way, so yes, so what you're saying is basically implicitly you're ending up with, sorry, I didn't fully understand your explanation.
Because you have like, let's say you have two tuples here.
Uh-huh.
So you like, if you join them, you get 4 tuples.
Yep.
So it's 2 by 2.
Mm-hmm.
Whereas like, so joining like gives you more than what you want because you're multiplying by the number of instances of each tuple. Does that make sense?
Sure. Yes. Right. So basically, both of these are correct. So what you're saying is that in some sense, when I decompose it down, there's a multiplicative effect of combining every tuple on the left-hand side and every tuple on the right-hand side, so we end up with more. What you're saying is also correct because B is not a key, and because of that, you are not able to sort of relate the tuples across the two relations, and therefore, you end up with spurious information. Another explanation or another intuition for this is that when you're decomposing down, you are taking the original tuples and breaking it down into fragments. So since you're breaking it down into fragments, you know those two fragments are going to join back to give you the original stuff. The only thing is those two fragments from two separate tuples may also join back to give you additional stuff. Right? So the fragments will still join, so you'll get back your original relation. The issue is that you'll get back additional stuff if you're not careful. Okay? Alright, so this is why doing easy decomposition does not work. Okay, so you get back bogus stuff, that's your issue. So there's a formal proof in the textbook about why the BCNF decomposition is lossless. I want to give you a little bit of an intuition for why that is the case via an example. So let's say I have a relation ABC and I have a functional dependency A implies C. Using this functional dependency, I can break it up into two relations, one corresponding to AB and one corresponding to AC. And then, let's say I have a tuple ABC in R. This decomposes into AB in R1 and AC in R2. Okay, since I'm exploring the multiplicative effect that you mentioned, I want to figure out if there are other tuples that also share the value of A but have different values for B and see if they join together to create spurious junk. Okay, so that's what I want to check. So let's consider the case where I have another attribute or another tuple which is A, B prime, C prime. Okay, let's say this is also in R. A, B prime, C prime will give us A, B prime also in R1 and A, C prime also in R2. Okay, so I have AC and AC prime in R2, AB and AB prime in R1. Okay, so I have two tuples. These have been broken down. I have two tuples in R1, two tuples in R2. Then when I try to recover the tuples in R, I now get, what do I get? I get all combinations, right? So I get this tuple AB joined with this tuple AB joined with this tuple AB prime joined with this tuple AB prime joined with this, right? So I get back 4 tuples. Okay, so I get back ABC, I also get back AB, C prime, AB prime C, AB prime C prime also in R, right? So the question is, are any of these bogus tuples? Are any of these not in R? And the answer to that is, as it turns out, because of this functional dependency, A implies C, all of these tuples boil down to the same original tuples. Okay, so if I have, since I have A implies C, if you take these two, okay, so since I have A implies C, I know that C prime is equal to C, right? C prime has to be equal to C since A implies C. Since C prime is equal to C, I basically get back ABC, AB prime C, AB prime C, and ABC, right? And these two are these two are exactly the same tuple. These two are exactly the same tuple. So I'm basically getting back ABC and AB prime C. these two are the original tuples that I started off with. Okay, so intuitively, if I break it down while respecting this property of this functional dependency, I get back the original stuff. I don't get back bogus stuff. Okay, so this is hopefully giving you a little bit of intuition for why this BCNF decomposition is lossless as opposed to other decompositions which might actually end up being lossy. Okay, any questions about this intuition? Again, this is not a very formal argument. It is just meant to give you a sense for why bogus stuff doesn't get introduced for BCNF, while if you just break it up into two attribute relations, you might get bogus stuff. Everything okay? All right. So yeah, so like I said, a full description, formal description of this proof can be found in the textbook, and it's essentially an extension of this intuitive argument that I mentioned. Okay, so the definition for a lossless decomposition is one, if we can recover the original relation after decomposition. So if you have R with ABC, you've decomposed it down to R1 and R2. When you try to recover it, you get R prime, which is equal to R ABC, as opposed to being a superset of R ABC. R prime, like we discussed, is in general going to be larger than R, but we want to ensure that R prime is actually equal to R. Okay, so those are the types of decompositions we like. So the two properties given by BCNF is it minimizes redundancy and it avoids information loss. Now, what is not preserved by BCNF, or what is not as much a guarantee provided by BCNF, is the preservation of dependencies and an ensuring of good query performance. So that's what we are going to look at next, at least number 3. Okay, so for the dependency preserving property, which is often important, while BCNF does not guarantee this dependency preserving property, the next normal form that we're going to discuss, which is a third normal form, or 3NF, does preserve dependencies. So that gives us a different point in the trade-off space. So this gives us a point which is more preferring dependency preserving as opposed to redundancy minimizing. Okay, but both of these normal forms are lossless, because if you don't have lossless, then you can have junk data. You don't want that. Both of these are lossless. Okay, so let's talk about dependency preserving. So let's say you have this this relation, phone, address, and name, and you have two functional dependencies. Phone implies address, and address name implies phone. Okay, so there's a BCNF violation, which is phone implies address, because phone is not a super key, and because of that we can decompose this into two relations. You have phone implies address, and phone and address as one relation, and phone and name as the other relation. Which functional dependencies apply to the first relation? Well, it's just phone and address. Which functional dependencies apply to the second relation? Well, there are no functional dependencies that apply to the second relation, right? So the only functional dependencies that we had were phone implies address and address name implies phone. So the first functional dependency applies to this, there is no functional dependencies. All right? So what happens then, right? So let's say I have this relation instance, which is phone address, has values 1, 2, 3, 4, 10 Downing, and 5, 6, 7, 8, 10 Downing, and the other relation with phone and name has tuples 1, 2, 3, 4 John and 5, 6, 7, 8 John. Okay. Now if I look at the functional dependencies overall, I have these two: phone implies address and address name implies phone. The only functional dependency that applies to this guy is phone implies address, and that is certainly satisfied in this instance. There are no functional dependencies that apply to the second relation, right? And therefore, there's nothing that I need to check with the second relation, right? So far we are good, because no local functional dependencies, no functional dependencies that apply to this guy or to this guy are violated. Okay, so far we are good. Now, when we reconstruct the original relation, we get these two tuples. We get 1, 2, 3, 4, 10 drowning John, and 5, 6, 7, 8, 10 drowning and John. But if we go back and look at this second functional dependency, which is address comma name implies phone, we find that there is a violation, right? So you have two tuples with the same values for the left hand side, but not the same values for the right hand side. So even though once you've decomposed it down into these two relations, the two relations themselves satisfy all of the local functional dependencies, when you bring it back to the overall relation, that relation may not satisfy all of the functional dependencies, right? Because this address name implies phone is a functional dependency that was not captured in any of the individual tinier relations, right? So there was no way to check that on the individual smaller relations. You can only check it when you bring all of the data back to the global larger relation, right? So that's an issue. So what this means is that this decomposition is not dependency preserving. Okay, so the decomposition basically loses the information of this dependency. There's no way of ensuring that this dependency is maintained. So, so like I said, this violates a dependency, and basically, why would we want, or what do we mean by preserving a functional dependency? If you have a functional dependency x implies y, and both x and y don't end up in the same decomposed relation, then that decomposition is not dependency preserving. That is a dependency that is not preserved. Unfortunately, there's no way to force the BCNF form to preserve dependency. So while BCNF gives us lossless join and tries to minimize the redundancy, it does not give us dependency preservation. Okay? So what do we do for this? So the alternative is the third normal form. The third normal form has the following property. A relation is in third normal form of 3NF if whenever there is a non-trivial functional dependency A1 through AN implies B, then either A1 through AN is a superkey for R or B is part of a key. Okay, so there's a new added OR clause which basically says if B is part of a key, then you don't need to worry about it. You don't need to decompose further. Okay, so in some sense this is more tolerant than BCNF. It is more tolerant than BCNF, and so it will decompose less. It will stop decomposing earlier. So for example, the phone implies address functional dependency will not cause a decomposition because phone is, wait, hang on, sorry, the address is part of a key, right? So if you go back to this example, you had address name implies phone, and because of that address is part of a key, so the phone implies address functional dependency will not cause this to be decomposed via 3NF, but it's still decomposed via BCNF. Okay, so I will stop here. I will wrap up 3NF and then I will move on to the next topic. Okay. Yes.